Hi, this is a short video of our NIPS 2017 paper on concentration of multilinear functions of the Ising model. So what is an Ising model? It is a probability distribution over n bit strings where each bit or node is plus or minus 1. The probability of a string x is given by the expression p of x. The theta parameters signify the direction and strength of the local correlation between pairs of nodes. For instance, a large positive theta value between u and v implies a strong positive local correlation. The Ising model is well studied and has applications in physics, computer vision, social network analysis, and neuroscience. It is a canonical example of a graphical model, in particular, a Markov random field. Albeit being well studied, it is hard to fully understand. For instance, it is intractable to compute the explicit PDF in many cases. Consequently, it is also not known how to sample efficiently from the Ising model in general regimes. In this work, we study concentration for polynomial functions of the Ising model. Since xi square is 1 always, any polynomial can be viewed as a multilinear function. These functions form natural statistics for fundamental tasks on Ising models, such as hypothesis testing and learning, and hence it is important to understand them. What is concentration? It is a well-studied phenomena which states that certain random variables lie in a small region with high probability, although they can take values far from this region. We study concentration for multilinear functions. Such functions are known to concentrate nicely when all the variables are independent. In particular, a degree d multilinear function, where each xi is an independent Rademacher random variable, concentrates at a radius of n to the d over 2 as shown in the figure. We show in our paper that a similar concentration holds for multilinear functions on Ising models as well, under a natural condition known as high temperature. Under this condition, we can also efficiently sample from the Ising model, and hence this is an important parameter regime. Without this condition, it can be seen that no non-trivial concentration might hold. Prior to our work, only a weaker concentration at a radius n to the d minus 1/2 was known for D-linear functions. Our work improves significantly over this bound. We establish a tight radius of concentration and a tight rate of decay of the tail. At a high level, our proof proceeds by using the evolution of the canonical Markov chain used to sample from the Ising model, namely the Glauber dynamics, to define a martingale associated with our multilinear function. Then we leverage advanced martingale inequalities to obtain the desired concentration result. Showing that d-linear functions concentrate crucially relies on the concentration of d-1 linear functions, which leads to an inductive style argument for the proof. We explore applications of our result to the problem of hypothesis testing. Unlike the standard setting where we have access to multiple samples, we study testing using a single sample from a well-structured distribution, for example, the Ising model on a grid. Take a look at these two pictures. One is generated according to an Ising model on the grid, the other is not an Ising model. Can you tell which is which? Our bilinear statistic can tell them apart, and significantly earlier than other common statistics such as the maximum pseudo-likelihood estimate, thus showing the usefulness of multilinear statistics. We also go on to perform an exploratory data analysis on last.fm network data using multilinear statistics. Full details are in the paper. We will also be presenting a poster at NIPS at this venue. Thank you.